In our last video of this section, we are going to talk about the span of a set of vectors. So the span, written as the span of V1 through Vp here in the definition, is the collection of all vectors that can be written in the form of our linear combination. So we're looking for all the vectors that span that space, with C1 through Cp being scalars. So starting at the beginning here, because I know I skipped the beginning, if V1 through Vp are an Rn, then the set of all linear combinations of V1 through Vp is denoted by the span of V1 all the way through Vp, and is called the subset of Rn spanned or generated by V1 through Vp. So Rn is the collection of all lists of n real numbers. N, if you remember, is the number of entries for each vector here, and P is the number of vectors that we have. So you need to make sure you get those variables straight. And this is related to our vector equation that we saw in our last video. If you remember, our vector equation, our linear combination equals to some b, has the same solution set as the linear system whose augmented matrix is each vector with the b on the right. Again, there's an imaginary line there. In particular, b can be generated by a linear combination of a1 through an, if and only if there exists a solution to the linear system corresponding to the matrix 5 here. So b is in the span of a1 through an if and only if this system is consistent. And that's what this little paragraph here talks about. So let's read that. Asking whether a vector b is in the span of v1 through vp amounts to asking whether the vector equation, this linear combinations with the v1 through vp equals b, has a solution, or equivalently asking whether the linear system with the augmented matrix has a solution, which means it's consistent. Which is exactly what we did when we looked at example 5 in the last video. Let's go back up here to example 5 from our last video again. We had a1 and a2 being these two vectors, and we had b. And we wanted to know whether b can be generated as a linear combination of a1 and a2. And the answer is yes. That means b is in the span of a1, comma a2. The answer was yes. We found it. We found a x1 and x2 that made this happen. Let's go ahead and look at an example that does not work. Let's look at this example. So we're going to let v1 be 1, 2, and v2 be 2, 4. Is b equaling 1, 3 in the span of v1, comma v2? Again, this is the same question as example 5. We could have said it this way. We could have said, determine whether b can be generated or written as a linear combination of the two vectors. So I rewrote it here, i.e., determine whether b can be written as a linear combination of v1 and v2. Or, i.e., another way of saying this, I'll put an or here, can b equal, a linear combination would be c1 v1 plus c2 v2. So let's go ahead and do that again. b is 1, 3. We know v1 is 1, 2. And v2 is 2, 4. And this equation here is the same as asking whether our augmented matrix has a solution. And we know v1 again is 1, 2. This is 2, 4. b is 1, 3. Which you can see that you can get from here, putting the right side all in one matrix. You can see here that this is the same thing as this, which we can write as an augmented matrix. So you can see that all does pan out. So let's go ahead and row reduce this. I'm going to take negative 2 times row 1, add it to row 2, put it into row 2 to get the first row doesn't change, and the second row is going to become 0, 0, 1. This is inconsistent. It does not work. If you think about this problem, you can see that it would not work, because if you look at what V1 and V2 are, V2 is just a multiple of V1. V1 is just 1, 2, and V2 is 2, 4. So it's just 2 times it. And B is 1, 3. So here's B. So you can clearly see that V1 and V2 does not generate B. There's nothing we can multiply V1 by or V2 by to get over to B. When you multiply something by V1 and add it to something else by V2, you're going to get something along this line. So the answer is no. B is not in the span because it cannot be written as a linear combination of V1 and V2. So what is the span of V1 and V2? It's just going to be that line. And you can see that by doing this. So let's look at that example. What is the span of V1 and V2, where V1 is the same two vectors above? V1 is 1, 2, and V2 is 2, 4. So what I would like to do is now find values of x and y so that the vector xy is in the span of V1 and V2. So again, being in the span of V1 and V2 just means that some constant times V1 plus another constant times V2 better equal to the vector. This time it's xy. Again, we know what V1 and V2 are. And that equals xy. That just corresponds to the augmented matrix 1, 2, 2, 4, and xy, the V1, the V2, and the xy. We can solve this by taking negative 2 times row 1, add it to row 2, put into row 2. We won't change our first row. Second row becomes 0, 0. This one would be negative 2x plus y. This is only consistent when negative 2x plus y equals 0. So y better be the line 2x, which, by the way, if I would have called C1 here x and C2 y, that would have been that line. So it is the points x, y, where such that, make that a such that, y equals 2x, and x and y are in the reals. Or you can call it some constant times V1. Or you can call it the span of just V1. Because the span of V1, by definition, is just a linear combination of all the V1. So it's going to be C1 times V1, or just you can call it C. So that is the definition. So let's look at a geometric description. Here's a geometric description of the span of just V. We're going to look at the span of V, one vector, and the span of two vectors. So the span of one vector is, we saw above, is C times V, where C is some sort of scalar. And where V is a non-zero vector, because if V was 0, then it would just, the span would just be 0. So I'm going to let this be V. And this would be some constant times V, or you can have negative V's. You can see it's going to be everything in this line. It's going to be a line. So the span of Z is a line through the vector V. Even if V is an R3, the span of V, again, is just the set of all scalar multiples of V. So which is the set of points, you make a V in the three-dimensional space. It's a set of points on the line in R3 through V and 0. You can see this figure. What about the span of U comma V? Well, we saw what happens when U is a multiple of V or vice versa. It turns out to be the line again. One a multiple of another. If it's not a multiple, so the span of U comma V, where V is not a multiple of U, you would have something like this. And we saw in our last video, when you take a linear combination of all those, you can get every point in the line, in the plane. So it's going to be the whole plane. It's going to be R2. The span of U comma V is going to be R2 when one of them is not a multiple of each other. That's what it looks like in R2. What about in R3? We have here, if U and V are non-zero vectors in R3, with V not a multiple of U again, then the span of UV is also a plane. It's a plane in UV. So you can hear this is an arbitrary vector U. Here's an arbitrary vector V. And we're going to add and subtract them and get any linear combination. And you can see when you take U plus V, you're going to get that plane right there. So it's going to be a plane that contains U, V, and 0. In particular, by the way, the span of UV contains this line. It does contain the lines U0. It contains the line V0, but also contains the line U plus V. So you can see this figure here. It says here it's a plane through the origin. Let's look at an example of that. So let's give a geometric description of the span of V1 and V2 for these two vectors. And it does not look like V2 is a multiple of V1 or vice versa. So let's just go ahead and find a vector. So I want to find an arbitrary vector B. I'm going to call it X, Y, and Z, where C1 V1 plus C2 V2 equals B. And if we plug these in and we figure it all out, it's the same thing as solving this augmented matrix. So let's go ahead and do that. So I'm going to go ahead and put this as an augmented matrix. B1 is 8, 2, negative 6. V2 is 12, 3, negative 9. And B is my XYZ. I'm going to make the 2, 3 my pivot to make my life a little easier. 2, 3, and Y. So I'll switch row 1 and row 2. I'll leave this last one alone. So then I'm going to take row 1, multiply it by 3, and add it to row 3. So I'm going to leave that first one alone. And I guess I'm getting a 0. I missed row 2, didn't I? Oh, but I get a 0 and a 0 here. And I get a 3y plus z. I guess I should do the first one as well. So let's do that. We're going to multiply the row 1 by negative 4 and add to row 2. So that would be a 0 as well. That would be a negative 4y plus x. So for this to be consistent, you need negative 4y plus x to be 0, and you need 3y plus z to be 0 as well. It's a z. So x equals 4y, z equals negative 3y. I guess I could solve for y for one of those. Plug y in to this one. Ah, it's not a plane. Guess it was wrong. Looks like a line. Looks like z equals negative 3/4 x. It's a line through the origin. So the span of V1, V2 is a line through the origin. Was one a multiple of the other? I think so. If you look closely, V2 is a multiple of V1. V2 is actually 3 halves of V1, and you can check it here.